Wow, that was really cool. I just appeared out of thin air, didn't I? Welcome to Weather Explained. I figured that during times where there are lulls in severe weather, I need to do something to keep the channel from dying. So, what are we going to do? We're going to talk about my favorite thing, severe weather. Today's topic, tornadoes. Tornado. Now, a violent, destructive, whirling wind accompanied by a funnel-shaped cloud that progresses in a narrow path over the land. Webster's 7th New Collegiate Dictionary. On the surface, this definition begs no interpretation. I could end the video here. Wait, no. I want you to leave this video far removed from the uneducated cur that you entered this video as, okay? It's a reductionist view of everything we find unique about these phenomena that have captured the hearts of so many, myself included. We're here to get into the weed, the mud, and the nitty-gritty. I present to you, what is a tornado? I used up all my cool editing magic. I'm not going to appear in the chair again. Anyway, big thanks to the people that let me use some of their footage for that intro for the video. All of their links are going to be in the description down below. Make sure to follow them on Twitter, subscribe to them on YouTube, because that wouldn't have been possible without them. To understand what a tornado is, you have to understand a couple of concepts that weather forecasters use to predict any kind of weather. Thermodynamics and kinematics. Now that might seem like big and scary words, but they aren't really overly complicated. This brings us to thermodynamics and kinematics. Long story short, kinematics is just a fancy way to say wind. Tornadoes need a special kind of wind to form though, and that's what's called wind shear. Wind shear is most easily described as a change in both wind speed and direction with height. It can be visualized in a handy dandy little chart called a hodograph. The hodograph shows all the cardinal directions, north, south, east, and west, just as a compass rose would, but there are several concentric circles which I don't have drawn here because I don't have anything to make a circle out of. And the further the point is from the center circle, or the origin of this graph, the higher in the atmosphere it is. Then you get to play a fun game of connect the dots to visualize your wind shear. The longer and more curved the hodograph is, the more conducive it will be for tornadoes. 3 Cape, or the cape found in the lowest 3 kilometers of the atmosphere, is a thermodynamic parameter that has the most impact on whether or not will be updraft strong enough to sustain a thunderstorm. 50 joules per kilogram of 3 Cape is considered adequate to produce tornadoes, and 150 joules per kilogram is considered extreme. This is of course assuming that your air parcel is surface-based, given the fact that tornadoes themselves are inherently surface-based phenomena. Next, the kinematic parameters that you want to look for is SRH, or Storm Relative Helicity. Values of 100 0 to 3 kilometer SRH are considered adequate for tornadogenesis, and values in excess of 300 meters squared per second squared can be considered extreme. Areas where these two parameters overlap on models are suitable for supercell and tornado formation, but keep in mind that most models are synoptic scale in nature, so the main mechanisms for predicting tornado setups will revolve around troughing and dips in the jet stream. A lot of your more microscale setups won't be able to be predicted until they come in range of higher resolution models, and sometimes the models don't even hint about those ingredients until the day of, or even hours before. But what are these microscale setups that I'm talking about? Well, usually, cape and wind shear are in a smooth gradient, but there are a few ways that the atmosphere makes itself unstable in a small geographic space. And first and foremost on that list is boundaries. You have a couple of boundaries that you could choose from, but for the sake of this video, I'll only be talking about outflow boundaries. Think of them as a miniature cold front made by cool air being expelled from a thunderstorm. The wind changes over a small geographic space can sometimes be what a thunderstorm needs to locally increase low-level spin in order to produce a tornado. A lot of coastal tornadoes will be produced by outflow boundaries from other pop-up thunderstorms impacting mesoscale meteorology of the other storms in the area. In fact, this tornado that I saw in Grand Chenier, Louisiana in 2020 formed under these conditions. The most useful parameters to use in forecasting tornadoes are all going to be derived from everything I've told you thus far. First, go to 500 millibars and find your jet stream. It'll jump right at you as an area of higher winds troughing and ridging over the map. Ideally, inside of a jet streak, like the one seen here, you would target the exit region where the divergence of the jet is the greatest. This is because there's a void of air in that area which causes air at lower levels to rise. Next, look for shortwave troughs that could help in convective initiation due to localized pressure height falls. Next, go down to the 700 millibar level and check for moisture. Does moisture overlap with the exit region of the jet streak? Moisture is a double-edged sword. On the one hand, if there's a lot of it, you can risk overconvection, which in turn could tamper CAPE and keep storms from being discrete. On the other, if there isn't enough, then storms might just never form at all due to entrainment of dry air. But if it's just right, then you have a weak cap that keeps overconvection at bay while only allowing the strongest updrafts to survive.
Nice.
The most optimal amount of moisture is a case-by-case basis, but usually a weak cap helps. Next, look at the wind streamers to find confluence bands, or areas where winds converge. They force air to rise in a subtle manner which could give rise to discrete convection. Next, go down to the surface to see what your initiating boundary may be. It could be a dry line which favors discrete convection due to weak forcing of air upwards, or it could be a cold front which isn't ideal due to stronger forcing. It could even be a remnant outflow boundary. Any amount of strong forcing can be overcome though, given favorable shear vectors. Ideally, you want shear vectors to be perpendicular to your initiating boundary to the tune of a 75-degree angle with a margin of error of around 5 to 7 degrees. The last thing I want to talk about is called streamwiseness. The idea here is that there's a common angle that you can get by drawing a line from your storm motion vector to any point on the hodograph, and then draw a line at 90-degree angles to the corresponding point on the hodograph. The closer that combined angle is to 180 degrees, the more streamwise your hodograph is. Long story short, the more streamwise your environment, the easier it is for a storm to stretch spin vertically to produce a tornado. For example, this hodograph is representative of the environment that Rolling Fork occurred in. As you can see, it's a straight line relatively far up into the low levels, and even when it's not an exact straight line, it is close to 180 degrees. So any spin could be easily stretched into the vertical in this environment, and so it's pretty indicative of why, the Rolling Fork tornado occurred so quickly after the storm crossed into this environment. I realized I've gone through this whole video, and the script doesn't mention anything about what a tornado actually is, so I'm going to ask the boys on Discord what they think. What is a tornado?
Okay. Big spin and it look cool.
Well, I suppose that now you have a surface level knowledge of what a tornado is and how to forecast it. And that's good for two things: chasing tornadoes and scaring girls away at the group function. You can thank me later. I hope you enjoyed this video, and if you did,